Okay, next on the big hit parade is the idea of psychopharmacology. In psychopharmacology, we try to study the effects of drugs on behavior. And obviously that's a big deal. A lot of people take psychiatric products to try to help their behavioral problems. So that is the field of psychopharmacology. One of the big issues that I mentioned before is this idea of type reductionism. Drug companies want to come up with products that will fix a neuron and maybe fix a behavioral problem. And so that's really the big issue. Can they actually do that? We have two different types of drugs. One is called an agonist. An agonist is a drug that mimics the neurotransmitter. My dad has Parkinson's disease. For Parkinson's disease, many times you take L-DOPA. L-DOPA is a product that will help the synthesis of a neurotransmitter. That's considered a dopamine agonist. An antagonist, when people have schizophrenia, you try to block dopamine. You give a product like Haldol, and Haldol will basically block dopamine at the postsynaptic receptor, and that seems to help people with schizophrenia. So the idea is you can give agonist and antagonist at each of the different steps in the neurochemistry part of the equation. Oh, did I mention neurochemistry as a term? Yeah, I did there. That was number 3. Neurochemistry is just how the chemicals work in your body. Psychopharmacology works by impacting the neurochemistry of things. So you can impact synthesis, release, binding, and even inactivation. The next big issue that I really wanted to talk about here was the idea of receptor subtypes. This kind of gets into the idea of reductionism in a way. A good example of this is pain. We know when people are in a great deal of pain, they take morphine. Now, does morphine work really well to help reduce pain? Yes, but one of the problems we often have is that morphine has a lot of side effects. And so one of the things the drug companies are pursuing is this idea that morphine actually binds to the neurotransmitter called the endorphins. And there seem to be different receptors for the endorphins. And so what the drug companies are trying to do is maybe if we just create a drug that will bind to this type of receptor shape, maybe it'll just fix the pain and not cause all the side effects. And that could be worth a lot of money potentially. It hasn't really happened for pain so much, but it actually has happened a little bit for the field of depression. In the old days, the first drugs used for depression, one of the products, as you look at the outline, was Nardil. And Nardil basically blocked the monoamine oxidases. These were enzymes that destroy the monoamines, serotonin, dopamine, norepinephrine, and so forth. They worked very well for depression, but because they were blocking so many different things, you couldn't have all sorts of foods. They were very unspecific. Many years ago, in the 80s, they came up with Prozac, Paxil, and Zoloft. Those are products that basically block the reuptake of serotonin. So it got a little more type reductionistic. If we could just block the reuptake of serotonin, that's almost like being a serotonin agonist. It puts more serotonin in the synapse, and that seemed to really help people with depression. And now we even have products like Effexor, which basically works with both serotonin and what's the other one? Norepinephrine, I think it says in this case. Let's see if I have it right. Blocking various things. So the drug companies are working on various receptor subtypes, hoping they can have type reductionism, taking a product that can fix the specific receptor subtype and then fixing the behavior as it would be. Hopefully that makes some good sense to you. Next, we actually go into the field of anatomy and neuroanatomy, but first we'll start with the outside part of anatomy, not neuroanatomy, but the peripheral anatomy, we have basically the sympathetic and the parasympathetic nervous system. The sympathetic basically works on the flight or fight system. If you're in an alarm state, your pupils will dilate, you'll get less saliva, you'll have increased heart rate, your bronchi will dilate. The parasympathetic nervous system is working when you're kind of calm down and relaxed with digestion and so forth. So that is the parasympathetic nervous system and the sympathetic, which are part of the peripheral nervous system. You can read more about that in your book as well. Yeah, that should do. Phrenology, I can just say this to you, I don't know if this is actually in your book, was the idea that the bumps on your head could tell something about what was going on in your brain, and that's really been disproven over the years, but it was there for a while. More importantly, the central nervous system. I want to go over that for you, and then we'll kind of wrap things up here. You basically have three parts to the central nervous system. You have first the spinal cord, which everything from the spinal cord goes up into your brain. You have three general areas. You have the hindbrain, the midbrain, and the forebrain. In the hindbrain, you have basically very primitive functioning going on there. You have the medulla oblongata. The medulla basically controls things like, I call it kind of the seven dwarfs area. Sneezing, coughing, refluxes, when you have to throw up, your medulla is kind of in charge of that. So the medulla is in charge of breathing, heart rate, and other things. The cerebellum is kind of behind it. The cerebellum has more neurons than any one structure in the brain. It controls movement. So if you've ever had experiences with alcohol, it affects your cerebellum, and it kind of causes problems for movement. The pons in the reticular formation affect basically arousal and sleep. And so they work very well together to try to wake you up in the morning. And there are lots of neurons and lots of things. This is the field of neuroanatomy. What is the structure and what does it do? In the midbrain, we have a few more structures. In the midbrain, one of the key structures is the substantia nigra. The substantia nigra basically has a lot of the brain's dopamine in it. And dopamine is very important when people like my father get Parkinson's disease. You start losing the dopamine in this area. The midbrain also has the superior colliculus. This is in charge of eye movements. And the inferior colliculus, because it has an inferiority complex. No, that was just a bad joke. It's in charge of finding where sound is going on and locating sound. The other very important structure that's not mentioned on here, but you can look in your book about it, is called the periaqueductal gray. That's where all the brain's endorphins are located, the periaqueductal gray. And the endorphins work for pain and pleasure. The basic idea is when you take morphine, it goes up into these areas and will cause you not to feel any pain. So we have the hindbrain, we have the midbrain, and then we have the forebrain. The forebrain is divided into some specific areas. We have basically the four lobes. We have the frontal lobe, which is in charge of higher order cognitive functioning. We have the parietal lobe, which is in charge of attention and areas of touch and sensation. We have the occipital lobe, which is in charge of vision, and the temporal lobe, which is in charge of hearing and acoustics. Below the lobes, kind of in another area of the forebrain, are the subcortical regions. These regions basically include something called the limbic system, kind of the emotion centers of the brain. We have the hippocampus, that's very involved with memory, the amygdala, which is involved with anxiety and anger and aggression, the hypothalamus, which controls the pituitary gland and all the hormones being released, and then the thalamus, which is basically the relay station of the brain. Your book actually talks a little bit about, on page 20, dendritic arborization. Has a picture of it. The more neurons you have in a given area, if you look at that picture on page 20, it basically shows a neuron with lots of dendrites. The more dendrites you have, the more likely that this area is really going to be working. So let's say somebody has had traumatic childhood experiences, your limbic system, the subcortical areas of your brain, they might have a lot of dendritic arborization in these areas that could cause some real problems for emotions. So that is the neuroanatomy perspective. The last thing I would like you to do, and this is kind of a homework assignment, is please go and add some extra information from your book about static and dynamic imaging and the stereotaxic procedure, basically pages 89 to 95, TMS, the stereotaxic, MRI, EEG, PET, and regional blood flow. Describe what they do and how they work and how they can actually be useful. So basically you have about 2 weeks to make an outline of this information. You can email me drafts. We're looking for not just notes, but a real detailed, structured outline. And you can have little paragraphs in here that describe things in your own way. So send me drafts of this, and these are kind of the basics of how the brain actually works. So hopefully this made sense for you, and thank you so much for your time and attention. Bye-bye.